Hi everybody, welcome to the series of videos on applied statistics, and today we shall talk about predicting with linear regression. Now this lecture will borrow on the notions such as correlation, functional and statistical relationships, so if you're not fresh with them, please consult the link in the description below. Also, I provide several other useful links in the description below that will support this lecture. So let's get going. Regression finds an association between a dependent variable y and one or more independent variables that we also call predictors. So in this case, the predictors are represented by names such as x1 through xn. Now, if you have attended the last lecture on correlations, you will understand that while correlation finds the strength of the relationship between the dependent and the independent variables, regression actually predicts what is the value of the dependent variable y for a given value of the independent variables. However, like correlation, regression cannot promise that the predictors actually cause the outcome. Hence the saying, correlation is not causation, also applies to regression. So you may say now that prediction is not causation. Note again that the actual relationship between the variables can be linear or nonlinear, and therefore regression can also be linear or nonlinear. But in this lecture, we shall focus only at linear regression. Now, if the data comes from a mathematical function that generates the data, then we have a functional relationship. In such cases, we can use regression to regenerate this function from the observed data set. Since we shall try to regenerate or guess the original function, it is possible that we may not find out the correct function. So we represent our guess with y hat instead of y. We assume that y represents the true function that originally generated the data. Suppose we guess y hat equals 2x represents our data, and the corresponding line fits the data exactly. Here 2 is the slope of this regression line. Changing the slope changes the function. For example, if y hat equals minus 2x, then it looks like this. Similarly, 2 plus 2x looks like this, and 10 minus 2x looks like this. So these lines have two constants. So we can generally say that our linear guess y hat equals beta naught plus beta 1 times x. Hence, we shall try to predict the outcome variable with a single input variable x, and the prediction formula or the regression line requires two parameters, that is beta naught and beta 1. The exact values of these two parameters will be chosen by the regression procedure that tries to find the best line that describes the data. Now, if it is possible to predict the data perfectly, as it may be the case when the data is coming from a known mathematical function, then the difference between the prediction y hat and the actually observed data y is 0, because our guessed function exactly matches the true function y. In practical statistical regression tasks, however, the exact prediction is rare. Our prediction so is still y hat that equals beta naught plus beta 1x, and the observed data is again represented by y, and they generally do not match. Instead, there is an error between the observed data y and our guess y hat. This error is represented by the Greek symbol epsilon, that is this funny looking e. This error is also called the residual. For instance, if our guess is represented by the straight line in the plot, then there is a gap between this point that we select now and the regression line. This gap is called the residual for this point, and in regression, we try to minimize the sum of all residuals for all the data points. Note, regression can be of many types. If we only have a single independent variable, we conduct simple regression. If instead we have many independent variables, we conduct multiple regression. Each of simple and multiple regression can in turn be either linear or nonlinear regression, depending upon what our parameters of regression look like. So let's see what that means. Note, when the exponent or the power of our parameters is at most 1, then the parameters are linear. So in the first example here, both beta naught and beta 1 have exponents 1. Hence, it is linear regression. Since we are using only a single independent variable, this is also simple linear regression. If instead we use multiple independent variables, then we need many more parameters, one associated with each extra variable. But the exponent of each parameter is still 1, so it is multiple linear regression. In nonlinear regression, the exponents of at least some parameters can be other than 1. For example, here beta 1, beta 2 are in the denominator, so their exponents cannot be 1, they're negative. Likewise, beta 3 is enclosed inside a sine function, so its exponent is also not 1. Therefore, finding the best values of these parameters to fit some data will involve some nonlinear operations. Hence, it is called nonlinear regression. Therefore, it is the nature of parameters that makes the regression nonlinear, not the overall function that appears on your screens. And that's a key thing to remember. Now, here's a question for you if you understood the last point well. Do you think this situation here requires linear or nonlinear regression? Notice, even though some of the variables involved are nonlinear, for example, we have x1 squared, if you focus at just the parameters, all the parameters, that is beta naught, all the way until beta k, are all linear because all their exponents are still 1. Therefore, we still require only linear regression. Finally, what do you think about this? Again, note, this is linear regression because all the parameters are linear. Now, here's an activity for you to think about. Find which situation demands linear or nonlinear regression. Leave your answers in the comments. Now, simple linear regression or even the multiple linear regression both have the same objective. They each minimize the squared errors between the regression estimate y hat and the actual data y. Hence, this process is called ordinary least squares regression or OLS. In essence, the sum of all the squared errors across all the data points is minimized. This process finds us the best line. It is also called the best fit line. In simple linear regression, this simply means estimating the best values for the two parameters beta naught and beta 1. The estimate for beta 1 is represented by beta 1 hat and is computed as per the formula on your screens. Here xi is the ith value of the independent variable x and yi is the corresponding value of the dependent variable y. X bar and y bar are the mean values of x and y. Once you have computed beta 1 hat, you can substitute it in this formula to compute the beta naught hat. In reality, we do not need to do it by hand. We simply supply the data set to softwares like R and they can do it for us via built-in functions. So the plot here shows two lines, each trying to fit a given set of data represented by small circles on this plot. Now, which of these two lines shall we use? Well, it turns out that the dashed line has a higher sum of squared errors. whereas the solid line has a smaller sum of squared errors. Now, the OLS procedure in the linear regression always finds the line with the smallest error, and in this case, it proposes the solid line. The source for this plot is linked in the description below this video. Note that regression and Pearson's correlation are strongly related. So much so that for a given data set, the sign of the Pearson's correlation and the parameter beta 1 that estimates the slope of the regression line are both the same. So for example, in the two plots here, B represents beta 1 and its sign matches the sign of R, that is Pearson's correlation, in both the cases. So when R is positive, the relationship is an increasing one, and therefore the slope of the line is positive. Likewise, when R is negative, as is the case in the plot on the right side, the relationship is decreasing. It's a decreasing relationship, and so the slope is also negative. Note the maths in this slide is just to prove the mathematical link between beta 1 and R. But the important thing to remember is that their signs are the same. If you are mathematically inclined and you want to verify that this relationship between beta 1 and R is actually provable, then you can pause the video here and go through the derivation steps yourself. Now, after we've got a regression line and its formula, we should be careful in interpreting it. Suppose we want to predict the cost of treating a patient with his or her weight. Now, suppose X is a great predictor, that is the weight. This is not necessarily true, but let's assume to make the point. Then suppose for a given data set, the regression line turns out to be like this. That is, cost, which is the dependent variable, equals weight minus 2. Here beta naught equals minus 2 and beta 1 equals 1. This looks like as shown in the figure. Now if we apply this formula blindly, then we can say that for a patient weight equals 0, the cost is negative. That means the hospital actually owes money to the patient for treatment. But how can that be true? Well, the problem is that we are over-interpreting our regression line. Clearly, in our data, we had no patient with weight 0 because simply such a patient cannot exist. Therefore, if we interpret our regression line outside the bounds of our data set, we can run into such troubles. Now, much like we conducted the hypothesis test for the correlation in our last lecture, we can also conduct a hypothesis test for our parameter estimates in regression. So consider this plot here that generates a slope estimate of minus 5.98. But we can question whether this estimate represents a statistically significant relationship that we can confirm via a hypothesis test. So our default or null hypothesis here is that there is no relationship. That is, the slope of line or beta 1 is actually 0. We can use hypothesis testing to see if our computed value of minus 5.98 actually significantly differs from 0. A way to do that is to compute a confidence interval around the computed value of beta 1. By this confidence interval, I mean that we'll generate two limits of values around the computed value of minus 5.98 using the formulas on your screen. Now, if the computed range of values includes a value of 0, which is what the null hypothesis assumes, then the computed value of beta 1 is not significant. And we cannot assume a relationship between the dependent and independent variables. So for example, if the confidence interval turns out to be between minus 7 and minus 3, then 0 is not within that range of values. And hence, we can say that the computed value of beta 1, that is minus 5.98, is indeed significant, and therefore we can assume a relationship between the dependent and independent variables. Instead, if the confidence interval were to be between -7 and +2, then that interval contains a zero value, and hence we fail to reject the null hypothesis, and we cannot assume a relationship between the dependent and independent variables based on the data that we have observed. For example, in this plot on the bottom of the screen, where we predict the grades of students by their heights, and in this the confidence interval actually contains a zero value. As you can imagine, this makes sense because clearly there is no relationship between student performance and their heights. Another way of doing the same is to conduct the hypothesis test directly. Again, the null hypothesis is that some parameter of interest, which is beta 1 in this case, equals 0. The alternative hypothesis can be any inequality, as in a standard hypothesis test. Then, much like we did in the correlations with the Pearson correlation, again we conduct a t-test with a degree of freedom equals n-2. Those who attended the lecture on correlations will note that to test the significance of Pearson's correlation, we also used the same degree of freedom. This again shows the correspondence between regression and Pearson correlation. Thereafter, we compute a t-statistic, as shown on your screens. And thereafter, we can compare it against critical values depending upon whether we have conducted a one-tailed or a two-tailed test. Alternatively, we can simply note the p-value and compare it with any significance level of our choice. Another way of confirming the significance of regression parameters is ANOVA, or analysis of variance. But that is the topic of another lecture. I do leave a reference below in the description for those interested. Now, if you have used simple linear regression and you have other variables in your data set, it is a good idea to plot the residuals, that is the epsilon values, against these other variables. This way, we can see if these residuals in turn have a relationship with these other variables in the data set. For example, here we are plotting the residuals obtained after fitting a regression line against an additional variable, that is weight. So weight appears on the x-axis. We can clearly see that there is a relationship between weights and the residuals because the residuals gradually increase as the weight increases. Now, if this happens, then this is a clear indication that we must include weight into our set of predictors and no longer depend on just a simple linear regression with a single predictor, whatever predictor we earlier used. So in these cases, we move on to what we call multiple regression. One word of caution before we wrap up this lecture. Note that R squared shows the strength of linear relationship when we do linear regression. However, if we are using multiple regression, it is possible to simply add more and more predictors that will each improve R squared only a little bit maybe. Notice R squared can never decrease by adding more predictors, simply because that if a predictor is bad, the regression procedure is smart enough to automatically set its coefficient or its parameter to 0 and hence nullify the impact of a bad predictor. Hence, we can make a large regression model with a high number of predictors, each of which is not individually a great predictor. Therefore, normally it is considered a good idea to generate a regression model with a small set of predictors that are each have a high predictive value. And to compare two different models produced by, say, different researchers or different students that have used a different number of predictors, we use another measure that is called adjusted R squared. And we use that instead of just the simple R squared. As you can see from the formula on your screens, the adjusted R squared is inversely proportional to the number of predictors in a model. Therefore, a model with a greater number of predictors will be at a disadvantage unless it produces an R-square value which appears in the numerator, and that this R-square value is much higher than that of another model. So with that, I conclude this lecture. Bye for now.